Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to discuss about the new topic stress strain curve for a different material. But we will discuss the ductile material in today's lecture. Remember that the ductile material it is also known as structural steel or mild steel or low carbon steel. It is known as low carbon steel because as the carbon content decreases, the material becomes more ductile. And if I increases the carbon content, the material becomes more brittle. Now what is the use of the stress strain diagram? Stress strain diagram, it is the characteristic of the material and it gives important information about the mechanical properties of that particular material and the type of behavior of that particular material. To find out the mechanical property and the behavior of material, we will require to perform a tensile test on a circular bar of standard specimen under the action of gradually increasing load. And that test we have to perform up to the failure occur. After the failure occur, we will plot a graph of load versus extension, because if I apply the tensile pull on any material, the bar will get extended. Therefore, under the action of load, we have to find out the extension of that particular bar. Now, how to find out the extension of that particular bar? The extension can be found out by using a device, extensometer. Extensometer, it is a device which is used to find out the distance between two definite points. This two definite point is known as gauge length. Or we can plot a graph of stress versus strain also. Now, this is a figure which shows the graph of stress versus strain. This particular figure is divided into number of points or number of parts. We have point A, we have point B, point C, D, E, F. Now we will discuss each point one by one. Point A is known as proportional limit. Point A is known as proportional limit. The name itself indicates what is proportional limit. Means stress is directly proportional to strain in this particular limit. If you observe a diagram from point O to A, we have a straight line. The straight line itself indicates that our value of stress is directly proportional to strain and the behavior of the material is linear one. It is a straight line, it means that it is the linear behavior. Now we will concentrate on point B. Point B is known as elastic limit. Now what is elastic limit? It is the value of the stress corresponding to point B. Remember that what is elastic limit? It is the value of stress corresponding to point B up to which the material behaves in an elastic manner. Material behaves in an elastic manner, it means that if I remove the load, then the material regains its original shape and size. If I increase the load beyond point B, we will get the point of yield. We will discuss the yield point. The yield point is nothing but it is the stress beyond which when the material is loaded, the plastic deformation of that particular material take place. All of you, as discussed in the earlier, plastic deformation is nothing but on removal of the load, the material does not regain its original shape and size. From figure, you can see that if the material is stressed beyond point B, the plastic stage will reach. And on removal of the load, it will not regain its original shape and size. At that point, for the same value of the stress, the material undergoes large deformation. Remember that beyond point B, the plastic stage will occur. Now we will concentrate on point C. Point C, it is known as upper yield point and point D is known as lower yield point. Now what is upper yield point? It is the upper yield point. At this point, there is an increase in strain even though there is no increase in the stress value. Means with the constant value of stress, there is further increment into the strain. The value of stress corresponding to point C is called as yield stress or yield strain. Now point D is known as lower yield point. At point D, the material again offers resistance to the greater extension and therefore the stress at D is called as lower yield point. You can see from figure at point D, the material again start offering the resistance to the externally applied load. Therefore, there may that particular material start taking the load again. You can observe from D to E also. Now we have point E. That point E is known as ultimate stress of the material. Now what is ultimate stress of the material? Ultimate stress, it is the maximum stress ordinate in a stress strain diagram. This E point, it is the maximum stress ordinate in the stress strain diagram. At E, the stress attains its maximum value, which is known as the ultimate stress or ultimate tensile strength or tenacity of the material. Remember that it is the largest value of the stress which is obtained in a tension test. This point E, it is known as the ultimate stress, and it is the largest value of the stress which is obtained in a standard tension test. It is found that the value of ultimate stress is found by dividing the largest value of the load. If I consider the value of load at point E, that load divided by the cross-sectional area of the specimen, it gives the value of ultimate strength of that particular material. This particular value of the stress is about 370 to 400 Newton per mm square. The value of the stress corresponding to point E in a ductile material is 370 to 400 Newton per mm square. At this stage, the cross-sectional area of a particular section start decreasing very fastly. At point A, the cross-sectional area of the specimen is start reducing very fastly, and this decrement in the cross-section is known as neck formation. This decrement into the section is known as neck formation. Now we have point F. Point F is known as the breaking stress of the material. Now what is breaking stress? It is also known as fracture stress, and the name itself indicates what is breaking stress or the fracture stress. It is the stress at which the specimen falls into two parts. Now, after the specimen has reached the ultimate stress at A neck is formed, which decreases the cross-sectional area of the specimen. And as there is decrement into the cross-sectional area of the specimen, that particular specimen, it broke into two parts. It gives, after failure of that particular material, it gives a cup cone type of ductile failure. Remember that after failure of the ductile material, it always gives the cup cone type of ductile failure. Now here it is the stress strain diagram for the ductile material. In the next lecture, we will discuss about the stress strain curve for the plastic and the brittle material. Thank you.